Okay. All right. So if you had your textbooks, you would find that today we're actually going to cover chapters 1 and 2 of the textbook. That being said, it's covering material that you probably have had before, even if you don't know that you've had it before, just by listening to particular ideas, particular concepts, and just by being involved in something. So it may sound like a lot to go through 2 chapters, but hopefully it's material that's not completely foreign to you, that it's something that you can actually build on. So this first question basically accounts for almost all of chapter 1. And remember, I told you when we take notes, we'll do it framed around questions. And since it's framed around questions, what do we call these questions? They're framing questions, right? That's wonderful. Like framing nails. How many of you do woodworking? For fun or just for any other, I don't know why you do it for other than fun. Maybe you do it to sell stuff. Okay. This is fun, right? And building picture frames, if you've never done it, you should try it, because you get to use these little nails, and they're just fantastic. When you miss what you're trying to shoot, and if your hand is in just the right place, you get the nail through the tip of your finger. But it's small enough that it doesn't cause a great deal of damage, just excruciating pain. And it's just, that's what I thought of when I saw framing. Again, I told you, I don't know, my brain's not going to work the way it normally does. So how does chemistry work? First part of this that we need to address is what chemistry actually is. Chemistry, by definition, is the study of matter. It's the study of matter. What is matter? Not what is the matter, right? Somebody's crying, like, oh, what is the matter? It's not what we're talking about, okay? What is matter? Yeah?
Like the molecules that form.
Yeah, it's not just even the molecules, yes, but it's everything. Molecules and not, it's everything. Everything physical in the universe is made of matter, okay? Everything physical in the universe is made of matter. Even space. Made of matter. So chemistry is the study of that matter. Now, as a science, would you all agree that chemistry is a science? This is called the homeschool science program, and it's a chemistry class, right? So as a science, it has to use the scientific method. Otherwise, it's not science. I don't know if you knew this or not, but for something to be science, it has to use the scientific method. That's how it works. That's what makes something science. So here is the scientific method. So I told you, we're 2 chapters. That sounded like real wind chimes. That is an amazing ringtone. Yeah. Wow, sorry. So the scientific method always begins by making observations. Always begins by making observations. I don't know, for example, on Mondays, students tend to be less prompt than on Wednesdays, right? Those are some observations. Did you say you too?
No.
Oh, no. I tend to be less prompt on Mondays than on other days. It's because the day before Monday, I mean, getting 3 kids ready for church, it's quite an ordeal, but it doesn't actually start all that early, right, compared to when I have to get here. So it's hard. It's hard to transition back to Monday, okay? So it begins by making observations. Then you explain the observation or observations that you made in a hypothesis. So again, my observation was students tend to be less prompt or tend to be more tardy on Mondays than on other days. Tardier? More tardy? Tend to be tardy more often. Let's go with that one. Tend to be tardy more often on Mondays than on other days. And then so I might go and explain it. Like, Monday is the first day of the work week or the school week. And that transition is what makes that so difficult. Okay, so there's my hypothesis. What's the next step? Somebody help me. I have forgotten.
Test the hypothesis.
Okay, good. So now that should say test if the hypothesis is true. Man, I need to change that. I'm sorry. You deserve better. I'm going to give you better. Test if, and then I'm going to add this to observation. There we go. There we go. So I added this because it can be more than one observation. You're welcome for that. Test if your hypotheses are true or false using a repeatable experiment. And that repeatable is a very, very important word there. Very, very important word. Using a repeatable experiment. Why does it need to be repeatable? You know what? Let's do this. Take 30 seconds, talk with those around you, and come up with a reason that the experiment has to be repeatable. All right? 30 seconds. Starting now.
Well, I mean, if it's a probability experiment, yeah, because I mean, if you get lucky one time, then it could be a different ending, outcome.
Yeah. Yeah, it makes confirmation possible. Yeah, it's good. All right. Why does it need to be repeatable? Any ideas? Anybody that wants to share your thoughts?
If it's not repeatable, then how can you prove that it's true? It needs to be.
Right, you have very little confidence that if you did an experiment and you can't repeat that experiment, you could never actually regenerate the same conclusions, right? You couldn't test it more than once. You couldn't test it more than once. Because anything can happen once. I mean, not anything, but lots of things can happen just once, and they may be very rare, extremely unusual circumstances, right? Let me give you an example. I will almost never, ever, ever be to this room any later than 12:40, which is 10 minutes before our class starts. Why? Because I know at least one of you is going to show up that early, and I want you to be able to experience how awkward it is for me to stand waiting for class and to not engage with you because class hasn't started yet, right? So I will almost never be here any later than 12:40. But one time anything can happen, right? Some student could, trip me on my way to class because of their hatred for me as a human being, right? I could fall down the stairs. That's actually a more likely thing. Do you ever try to walk downstairs while typing out an email? It is really challenging. Like, it's one thing to write an email on a phone while you're walking down the stairs because we regularly have our phones in our hands doing things while we're walking. But trying to type an email on a computer while walking downstairs, it is challenging. Let me tell you. Last time I did it, I fell down the last 3 stairs here. It was awesome. In front of a whole bunch of people. It was great. Probably one of the greatest experiences of my life. Okay? It's good times. Okay? But one time, really unusual events can happen, right? Anyways. So, if the hypothesis is right, then it has the potential to become a theory. So if you came up with a hypothesis to explain your observations, you tested that hypothesis with a repeatable experiment so that you could do the experiment over and over and over and over again. And other people could do the experiment over and over and over again. Then it has the potential to become a theory, which is a well-supported hypothesis. Hypothesis well-supported by the data, by the results of your experiments. Does that make sense? Have you all seen this before? Scientific method? Maybe? Or you've read something and you're like, I got this. This is simple. This is baby stuff. You might be right, but we'll get to some grown-up stuff soon. Don't you worry. We'll get to some stuff that'll take your teeth to chew, right? This you can chew with your gums. You don't like that illustration? That's a great analogy. If the hypothesis is wrong, then it gets replaced by another hypothesis. Now you have to come up with some other explanation for your observations. Welcome. Okay, does this make sense? Right, your hypothesis is an explanation for what you saw. If you test it and it turns out to be wrong, you need a different explanation for your observation. Okay. Yeah. So chemistry is a great tool for learning about matter. I mean, it is just an incredible tool, right? It's the study of matter, and it is a phenomenal tool for learning about matter. However, you have to understand that since theories and hypotheses often get replaced, we have to put chemistry into a different category than what we put scripture. Okay? So theories and hypotheses, again, can be great explanations for what you see. But we have to put it into a different category than God's Word, than Scripture, because of the fact that theories and hypotheses may change when we have some new data. Okay, I want to give you a series of observations. Okay, and we're gonna use the scientific method. Okay, are you ready? I was gonna do anyways. I'll do one that's from chemistry. Okay. So water freezes at 0 degrees Celsius. Wow, 0 degrees Celsius. Okay? Which is 32 degrees Fahrenheit. But anyways, we're going to use Celsius because you tend to use the metric system in science. Okay, water freezes at 0 degrees Celsius. Water can be liquid and solid at 0 degrees Celsius. Okay? Ice cannot exceed 0 degrees Celsius. So you can't get ice at a temperature above it, but at 0 degrees Celsius you can have both water and ice, and water begins to freeze at 0 degrees Celsius. Okay? So here are your observations. Relatively simple observations, not an enormous amount of data there. And I want you to, from these observations, I want you to come up with a hypothesis that explains it, especially this one here. That water can be both solid and liquid, meaning you can have ice at 0 degrees Celsius and liquid that's at 0 degrees Celsius. That's interesting. Okay? So explain this a little bit. See if you can come up with a hypothesis and if we can think of some ways that we might test that. Okay? Take 3 minutes and I'll circle around, spend some time talking with those around you and see if you can come up with an explanation for what you observed. All right? 3 minutes. Starting now. What is this? 8:18. 8:18. Gotta chew on that one for a while. You have any thoughts about this, Josh? Layers? Okay, what do you mean? Okay. Yeah. Yeah. Absolutely. Absolutely. So that because they separate, you can end up getting that waters can be both liquid and solid. That's zero degree Celsius. It's good. I like it. You thinking? You already got it? Yeah. Excellent. Yes, class. Okay. I like that. I like that a lot. I like that a lot. Will you share that with everybody if nobody else shares that with you? Yeah, I'll share. Do you mind? Can I credit you? All right. What are some thoughts? What are some explanations for these observations? Or maybe just one explanation. You don't need multiple. I apologized last week, right, for the level of interaction you're going to have to get comfortable with. Did I do that? Was that one of my apologies? Okay. Jonah.
Water doesn't freeze instantly, so it could be liquid before it freezes at 0.
Yeah, right. It takes time. Your whole collection of water is not going to freeze all at the same time. Right? You have to think a little bit about what's going on as it changes from a liquid to a solid. And that can't happen at the exact same time, so it's a process, right? Some of the molecules are going to get locked together, and others are still free. It takes some time. Yeah. All right, so there's a hypothesis. Do we have any others? True or false? Ice is cold. True. Good. We're on the. Oh man, we are making enormous progress. I love it. Did you hear how many people said true there? That was fantastic. You were capable of interacting. I love it. Okay. So true or false? Ice is cold. You all said true. Not everyone. Some people held out. Okay. Why is ice cold? True or false? Energy is leaving your hand and entering the ice when you touch it. True or false?
True.
True. That was a little bit less confidence. I heard the true, like with a question mark after. It is true. That's why it feels cold. Energy is leaving your hand and entering into the ice cube when you touch it. Okay, that's why it feels cold. You're feeling that energy transfer. Okay. Another hypothesis might be that energy has to be released from the liquid water in order to get it to change into a solid. Okay? Does it make sense to you that in a solid object, the molecules or the compounds, whatever's making it up, are locked together? Does that make sense to you? Because if they weren't locked together, you should be able to just push them apart very easily, right? But if they're locked together, you should get some resistance, right? So you can pound it and it sounds impressive. Although pounding liquid sometimes sounds impressive as well. It's like, you know, it depends on what the... If you ever like just punch like a plate of whipped cream, although that's not really a liquid, that's a liquid medium with... No, that's a solid medium with liquids anyways. That's something a little bit different. Or just like punched a bowl of water. No? It's actually really satisfying. You know, like punching a wall, there's something satisfying about that because it relieves some tension, but then you break your hand, right? And that's not satisfying. But punching a bowl of water, you don't break your hand, right? Does this make sense? Okay. Because I just don't know, like, I don't know if I'm speaking nonsense or whatever. So another hypothesis might be we need to get some energy out of liquid water before it can freeze. Because that liquid water, the molecules are free to move around. That's what makes it liquid. But if you're going to make it ice, they're no longer free to move around. So we've got to take some energy out of that, and the energy isn't going towards lowering the temperature, it's just going towards stopping the water molecules from moving. It's another potential hypothesis, right? A little bit more sophisticated of one, but it's just a little different. Okay? Make sense? We feel okay about this? coming up with the testable hypothesis, it's a little interesting, right? So based on your hypothesis, Jonah, I would predict from that then the more water you have, the longer that process will take for all of it to freeze. Does everyone agree that out of Jonah's hypothesis that makes sense? We could do a very easily repeatable experiment about that, right? Take a cup of water, put it in your freezer. Figure out how long it takes for it all to freeze. Take a bigger cup of water, put it in your freezer. Figure out how long it takes it to freeze. Put an even bigger cup of water, right? And then next thing you know, you're putting like a bucket of water in the freezer, taking everything out to make room for it. And you don't worry about that stuff, thawing out and going bad. If it was in the freezer, you didn't really want to eat it anyways. If you wanted to eat it, you'd be eating it, right? My sister-in-law works for Ruiz Foods, which probably means nothing to you until I tell you that they make El Monterey breakfast burritos and other burritos. Have you ever had any El Monterey microwave burrito? No? Well, my sister-in-law, anyway, she works for the company that makes them. But her freezer is absolutely packed full of these microwave burritos. That some of them have gone to market, some of them they didn't make it because people really didn't like them. So they're like, yeah, people don't really want to eat these, so we're not going to sell them. And then she's like, oh, I'll take them home and put them in my freezer. But nobody eats them there. And then so her freezer is just full of stuff. Anyways, that's why I said if you wanted to eat it, sorry. All right, so how does chemistry work? We need to answer the framing question, okay? How does chemistry work? And you would answer that by saying it works by studying matter. Chemistry works by studying matter. Chemistry works by studying matter. Chemistry works by studying matter. Do we have any questions about that? I have no key terms for you for this one. So I told you on the right we would do the answer to the question in key terms. I have no key terms for you, okay? You're free from key terms. The next question we're going to address is this one. What can we measure? Sorry, the truck was bothering me. Wow, the door is taking forever to close. Okay, what can we measure? Some of this we saw last week a little bit. We can measure the amount of matter in an object. We can measure the amount of matter in an object. We call this the mass. Do you remember we did this last week? Y'all took a field trip over to our balance and just had the incredible experience of watching it provide the mass for that rock, right? It's transformative. Changed your day, renewed your outlook on life, right? Provided you hope for the future. That was sarcasm, by the way. I need to tell you a story. I may have told some of you this before, but we had 2 foster kids for 6 months. And my kids are 7, 5, and 3. And then the foster kids are now 6 and 4. But at the time that they were with us, our kids were 6, 4, and 2, and they were 5 and 3. So we had 5 kids, ages 6, 5, 4, 3, and 2. Okay? It's just outrageous. Lots of really hilarious things happening all the time. So my oldest daughter's starting to really understand sarcasm. And enough to where like she's starting to be sarcastic about things. So we were driving by the dump one day and I was like, wow, it really smells great. And then she laughed and she said, Daddy, that's sarcasm, isn't it? And I was like, yeah. And then so the older foster boy, he says, wait, let me try. And he's like, great sand there. And then he's like, did I do it? Did I do it? Was that sarcasm? And my daughter goes, I don't know if that was sarcasm, but that really wasn't very funny. And it was like my proudest moment as a father. Like better than anything else, like any of my kids have ever done. That was my proudest moment actually, that's not true. It was my second proudest moment as a father. Same kid, our oldest, it was on her birthday and we were in a grocery store and I said, you can pick any treat you want. Anything you want. It's your birthday, right? Go nuts. You know what she picked? She picked a Slim Jim. And I cried. I was so proud of her. Like anything. She could have picked anything. And she picked a Slim Jim. Like that was just, like what 4-year-old wants a Slim Jim on their birthday? My daughter. All right. So we can also measure the amount of space an object fills. We call this the volume. We also saw this last week. Really, we did. You guys put water into the graduated cylinder, right? Look at that. We have shared experiences already, shared history. Gosh, we go way back. Now we're starting to get something. This is good. Okay? I know it's Monday, and it's like right after lunch, and you're like, this is normal nap time. Like I have it scheduled in my day as like nap time from 12:50 to 1:45, and I'm taking that away from you. I understand that. But, we can still interact, right? Make the sacrifice worth it. Because if you just sit here and are like miserable the whole time, then you're sacrificing your nap for nothing, right? Invest in it. Make sense? Okay, cool. We can also measure the mass divided by the volume, right? If we measure the mass and we measure the volume, we can measure the mass divided by the volume, and we call this the density. This is what we did last week in our introductory lab. I was going to say fake lab, but it wasn't fake. Introductory lab. And why do we care about the density of an object? Do you remember that? I asked you at the end of our time last week, I said, why do we even care? Like, what could we even do with the density of an object? Do you remember? Nobody? You're really requiring two things. One, that we remembered, which is Monday afternoon during nap time. It's hard to remember anything. And then two, you're expecting me to actually share my memory, and I have to risk being wrong. If you know the density of an object, you can compare it to known densities and figure out what it's made of. Right? Remember I had this rock and we're like, what is it made of? There's so many different things that rocks are made of. Well, if you knew the density and you compared it to known densities of materials, you can figure out what that rock was made of. Why would you care what the rock is made out of? Do you remember that? I told you this too. So you can know if you ought to build a wall with it. Right? Or use it to make projectiles that you're going to fire out of a slingshot. I didn't tell you that one last week, but that's a new one that just came to me. You're welcome. Right? You don't want things to just completely crumble when they hit something, right? Because if you're using a slingshot to knock beehives out of trees so you can get the honey, right? You need to know that you've got satisfactory density so you can generate enough momentum. Have any of you ever done that? Have any of you ever seen the cartoon beehives that hang from a tree branch? Have any of you actually seen a beehive that looked like that in real life? It's spectacular. If you haven't, you need to experience that. You need to go after this class is over, and you need to go on a tour of somewhere where they have those kinds of beehives. It's just so cool. You're like, oh my gosh, it looks just like a cartoon. It's like, where's Winnie the Pooh? Where's he going to show up? We can also measure the distance between 2 points, and we call this the length. We measure the distance between 2 points, and we call this the length. We can measure more than this, right? We can measure temperature, and what are some other things we can measure? You can measure the amount of time something takes, right? I know you're sitting there, you're like, this. I've certainly been in this room for longer than 40 minutes. But you haven't. You really haven't. Actually, it's only been 35 minutes, I think. 35 minutes. You're like, wow, it's so amazing how, when I'm skipping through a park, time just flies. But when I'm sitting in here, it's just dragging on. Do any of you skip through parks? There's just something if it's the next time you're having a terrible day, I don't know, maybe the Dodgers are losing again, or USC is losing, just getting destroyed by Texas again, and you're like, I'm having a terrible day, just start skipping and something changes. I mean, it's like you can't skip angry. It's like as soon as you start skipping, a smile comes on your face, right? You imagine yourself having one of those big giant lollipops you get from, Knott's Berry Farm or something with all the different colors, Just try it. All right, so what can we measure? The answer to this is anything we want. I mean, literally write that over on that smaller side of the column. Anything we want. Anything we want. What can we measure? We can measure anything we want. And because you'll know reading that we're assuming that it's made of physical matter, right? Like I can't measure how bored you are right now, but that's because that's not physical matter. That was a joke. All right, so a couple of key terms. If you would do me the favor of defining density, and we've seen this a couple of times, but I want you to go and actually look it up and see if you can find anything novel or new or unique about this. Density and then length. Density and length. If you'd go and take some time to define those, it'll be fruitful. It'll be fruitful. All right? We're now all the way through chapter 1. Look at that. In 38 minutes, actually we started class late because we were waiting for others to show up. So like 35 minutes of time and we've gone through a whole chapter. Look at that. It's powerful. Y'all have accomplished so much. Next question. How does density work? How does density work? How does it work? How does density work? First off, we measure the mass of an object, typically in grams. Measure the mass of an object, typically in grams. That's the first part of how density works. First, you got to know what the mass is, and you measure that typically in grams. Not always in grams, but typically. What's the next thing we do? Y'all know this. Somebody's got to share it. We need this interaction. Abby. We measure the volume. We measure the volume, typically in liters. Okay, we measure the volume typically in liters. And then we go and divide the two. We get density in grams per liter. So now we know in every liter of that material, we have this amount of matter. This amount of mass. This is transformative stuff, right? It's like the things that you're going to go and tell all your friends about. I mean, you probably don't talk to people anymore. You'll just put it out on Instagram or, Snapchat. Some other, platform that I don't know anything about. Do you still talk to people? That was a joke. Gosh, it's rough. I'm trying my best. This is all I got. So, because 1 liter is actually quite a bit of fluid, we oftentimes use milliliters in the lab. A liter of fluid is actually quite a bit of fluid. Let me show you a liter of flask. So here's a liter flask. It's a pretty good amount of fluid. If you're dealing with something, and you're going to do a real chemistry lab, and you're dealing with something that's fairly volatile, and remotely dangerous, this is a lot of it. This is a lot of material. Okay? I know what you're thinking, all right? Why wouldn't we deal with a lot of it? Because if it's dangerous, a lot of it means it's even more dangerous, and that's cool. It's true. but it's unnecessary because a smaller volume will give you just the experience. Right? And so what this all boils down to is this. The more dense a material is, the further it's going to sink compared to less dense materials. So the more dense a material is, the further it's going to sink than less dense materials. So we've got this picture here. Who knows what's in this picture? Oil and what else? And water. So you got oil here and water here. They are separating because they have different densities. Which one's more dense? Water. How do you know? Because it's on bottom. It's saying deeper than the less dense material. Look at that. You already understand density. Look at all you've accomplished. This is incredible. All right? So how does density work? Basically write C last point. S-E-E. Last point. S-E-E. Last point. Because the last point here basically tells us how density works. The first point tells us how we measure density and what we measure density in, but the last one tells us how it works. The more dense materials sink deeper than less dense materials. Marble is an incredibly dense material. Okay? Marble is an incredibly dense material. But the Greeks loved to build with marble. And they just loved it, right? It was such a wealthy empire that they loved to build buildings out of marble. So when they would take conquered people in through these cities, they would just be like dumbfounded that they were so wealthy that they could build something out of marble. But marble is super dense. And so these buildings sink every year, deeper and deeper. And so you go and see some of these really old marble buildings, and you actually have to step down several feet to get in the building. And it hasn't always been that way, but it's so dense, it's sinking into the earth. It's so awesome. Right? Whoa! It's okay. Just relax. Okay. So you don't have any key terms for that one either. How does length work? How does length work? Well, just like density, we need to measure. We need to take some measurements. Okay, what do we measure for density?
Mass and volume.
We measure mass and we measure volume. Length is nice because all we need to do is make one measurement, and we measure the distance between 2 points. And we measure this typically in meters. Typically in meters. Now, these 2 points can be on the same object. So if you wanted to know how long or how tall this Erlenmeyer flask is, you can measure the distance between 2 points, one on the very bottom and one on the very top, right? But we're still measuring the distance between 2 points. Those 2 points just happen to be on the same object. Or that object might be you. And every year when you get your physical, they measure the distance between 2 points again. And every year you're like, man, I wish I grew a little bit more this year. Unless you're like, I'm perfectly satisfied with my height. Anyone feel that way? My younger brother is 3 inches taller than I am. That's just messed up. That's just messed up. I mean, now it's not really that big of a deal because I'm a grown man. But when we were kids, it upset me. But it's okay, I outweigh him by 100 pounds. So it's like, you know, it all rounds out. It all rounds out. Well, not for him, it rounds out for me. Now, because 1 meter is such a large measurement, oftentimes we use centimeters. Okay? In the lab, we're going to usually use centimeters because meters are over 3 feet. It's like a little bit over 3 1/4 feet. It's okay to laugh about that. I see some of you are like, you're trying to suppress the laughter. It's okay, right? I told you, if I make fun of myself, it's fair game to laugh about it. It's good stuff. So in a lab, we're rarely going to use a meter because it's 3 1/4 feet. That's a huge distance between 2 points. Okay, we'll usually use centimeters. Centimeters. All right. That makes sense? So how does length work? Just write it's the distance between 2 points. How does length work? It's the distance between 2 points. Again, it's the distance between 2 points. And I would like for you to define meter, M-E-T-E-R, but make sure you look up meter and length. Otherwise, it's going to just define a meter as like a machine used to read how much electricity you use or how much gasoline you use. So look up meter and length, okay? Because hopefully in the definition you'll find the origin of meter. What is actually a meter long that gave us the original measurement? You know, in the US system we use a foot, and that's because whomever provided the foot for that measurement, their foot was exactly 12 inches long. It's like, who knew? Who knew? All right, last question we're going to deal with is this one. How can we change units? How can we change units? How can we change units? And so I've mentioned to you a few times, because this unit is too large, we'll usually use a different unit. But what if you needed to change between the two? Like for instance, you wanted to know how many milliliters are in a liter. Or you wanted to know how many centimeters are in a meter. How do we do that? How do we make that change? I'm glad you asked. I'm glad you asked. Here's how we do it. In our system, we do it using just crazy ratios that don't make any sense. Like a pinch. Have you ever read a recipe that said use a pinch? A pinch is 1/8 of a teaspoon. Or a dash, 1/16 of a teaspoon. Why? I have no idea. I think that there are 3 teaspoons in a tablespoon, but it's not even perfectly 3. It's like 3 and a smidgen. I don't even know what a smidgen is. I just made that one up. Right? How many cups are in a pint? 2. How many pints are in a quart? 2. How many quarts are in a gallon? Should be 2. It's not 2. It's 4. Right? It's like just these ratios, they're just so silly. It's like how many inches are in a foot? 12. Cool. How many feet are in a yard? It should be 12. No, it's 3. Right? It's like it doesn't make any sense. These ratios, it just all seems made up. Like somebody was just like, oh cool, like we'll just kind of make up arbitrary measurements. How many feet are in a mile? 5,280. How many yards are in a mile? 1,760. Why? I don't know. It's just the way it works. But in the metric system, it all makes sense. It all makes sense. And we change units using prefixes. We change units using prefixes. All right? It all makes sense. And if the US system makes sense to you and you're offended by my treatment of it, I'm sorry. But it really doesn't make any sense at all. It doesn't really make sense. It's just you're comfortable with it. It's really what we're getting at. Maybe you're not comfortable with it. It's good. Okay, so let's say a meter was way too long, and you're like, I don't need a meter, I need something that's about 1,000th of a meter. Well, that's perfect, because we have this prefix that is m, which equals 1/1000th of whatever the unit is. So a millimeter is 1/1000th of a meter. A milligram is 1/1000th of a gram. A milliliter, guess what? It's 1/1000th of a liter, right? It's so perfect. So perfect. And you're like, 1/1000th, that's small. Like, how do I even do that? That's okay, we can deal with that. But at least it makes sense. You're like, I need a little bit more than a millimeter, so I'm going to use this prefix, C, for centi, and it's 1/100th of a unit. So a centimeter is 1/100th of a meter. A centigram is 1/100th of a gram. What about a centiliter? 1/100th of a liter, right? It's so predictable and nice and orderly. You're like, oh, I need even more than that. So we'll use a deci. Like a decimeter. 1/110th of a meter. A decigram. 1/10th of a gram. A deciliter, what do you think that is? 1/10 of a liter, right? It's so nice and predictable. But you're like, no, I need bigger, right? I need bigger. So then we can use prefixes that are more than a unit. The prefix K is kilo, and it's 1,000 units. So a kilometer or a kilometer is 1,000 meters, right? And a kilogram is 1,000 grams. And a kiloliter is, guess what? It's 1,000 liters. Look at that, critical thinking. You guys are awesome. And I showed you what a liter is and 1,000 of those. You're like, that's incredible. Like 1,000 liters of soda. You can do a lot of damage. Oh, you didn't have a question? No. Okay. Mega, M for mega is 1 million units. 1 million units. So a megameter, 1 million meters. A megagram, 1 million grams.